So before starting with the new topic, that is parallel processing architecture for FIR filter, I would like to slightly recap the concept of pipelining. So I had started with this filter direct form, which is represented by this equation a of xn plus b of xn minus 1 plus c of xn minus 2, and the minimum clock period was equal to minimum sampling time, and that was in turn equal to critical path time, and the critical path time of this direct form was tm plus 2ta, and we have applied pipelining. So so if we put two delay elements along this feed forward cut set, then the critical path time was reduced to ta plus ta, and further it can be reduced to tm if delay elements were placed along this feed forward cut set. Okay, so the main aim was to increase the sampling rate, and this was achieved by reducing the sampling time, and this was in turn achieved by reducing the critical path time, because these are dependent. So the filter that we have taken is a kind of a single input single output system, which takes one input sample. Let's say the input is x1, it will process it, it will take some time t, and it will generate a corresponding output y1. Then we will provide a second input sample, let's say x2, it will process it by taking the same amount of time, and it will provide output y2. And this processing time t can be reduced by pipelining. So till now we have till now we were successful in reducing this t by using pipelining. So now my question is, what if we have pipelined the single input single output system in every possible way, and let's say that we have achieved processing time t dash, which is less than t. So this t dash corresponds to the pipelined system, and we have pipelined the system in every possible way, and there is no way to reduce this time beyond this t dash. So now sampling rate of this pipeline system is bounded at this t dash, so it will be 1 by t dash. There is a lower bound to this sampling rate. Now what if I further want to increase this sampling rate? Okay, so we have exhausted the possibilities of pipelining the system, and now we have to find for some alternative way. So the answer is using the concept of parallel processing. Okay, so that we are going to discuss. So we will be converting this structure from single input single output to multiple input multiple output, that will take multiple samples, let's say n sample, and produce multiple output. So the second reason why we need a concept of parallel processing, because let's understand this by this taking this two circuits. So this is a transmitter which is generating some signal, and this is a receiver, and these two are connected by a wire. So now let's say that output pad delay plus input pad delay plus this wire delay is 8 nanoseconds. Means if this chip generates a sample after processing it, so this sample will take 8 nanoseconds to reach to chip 2. Okay, so this sample 1 has to move from output pad, then it has to travel via this wire, and then input pad will receive it, and then it will transfer it to chip 2. So this sample cannot escape this route, so 8 nanosecond is required, and that too after it is processed by chip 1. Okay, now let's say that critical path time of chip 1 is less than 8 nanosecond, and the critical path time of chip 2 is also less than 8 nanosecond. So no matter how much fast it processes the sample 1 after receiving, let's say the critical path time is, let's say, 6 nanosecond. Okay, so after receiving the sample, it will process this sample in 6 nanosecond. Okay, so now the next sample will arrive after 8 nanoseconds. So for 2 nanoseconds, this chip 2 will be in idle stage. Okay, so no matter how much you optimize it, if you optimize the critical path time to 5 nanosecond, then it has to wait for 3 nanosecond, because it will process the sample 1 in 5 nanosecond, but still the traveling time of sample via this path is 8 nanosecond. Okay, and the same applies to this chip 1. No matter how much faster it generates the samples, it has to wait till the sample will reach to this chip 2. Okay, so this is the problem. We say that this system is now bounded by the delay of this communication channel. This is a communication bounded system. Okay, so at this point we need parallel processing to further increase the speed of this architecture. So the concept of parallel processing is very simple. It just says that use duplicate hardwares and make them work in parallel to increase the sampling rate. So starting with a single input single output system, so the input is xn, and the corresponding output is yn, and let's say that its t clock minimum is equal to t sampling minimum is equal to critical path time, and that is t. Okay, so this thing has been already derived. Now if the input to the system is x1, the output will be y1. Okay, after the processing time, the input is x2 and the output generated will be y2. Now I am using two systems. Okay, and if the input to the system is x1, okay, at the same time I can give input to this system also. So the next sample with respect to x1 will be x2, and the output generated will be y1, and the output generated at this point will be y2. Okay, and the time for this generation of corresponding output will be t. So in this case, in t time, one sample was generated, and in this case in t time, two samples are generated. Okay, so t clock is the same. Whatever was the t clock for this system, this will be driven by the same clock speed, and this will be driven by the same clock speed. I am not changing this clock speed. Okay, so since this system is driven by the same clock speed t, so it will take t amount of time to generate y1 corresponding to s1, and the system will also take the same time provided by driven by the same clock speed. Okay, but since we are using two hardware in parallel, in t time two samples will be generated, and we can say that sampling rate is doubled. Okay, talking about its critical path time, so the critical path time for this system is supposed to, so the critical path time of this system will be the same, because this is nothing but this system, and the critical path time of this system will be also t, because just we are using the single input single output system in parallel, that's it. Okay, so t clock for this system will be t critical path time for the system will be also t. So what is changed? T sampling. T sampling for the system is reduced by 2. Now we are getting two samples in same time. Okay, so sampling rate is doubled. So in this case t clock is not equal to t sampling, and t sampling is t clock by 2. Okay, yeah, t clock is equal to critical path time. This is not changed. T clock will be equal to critical path time, that is t. So what is changed? The sampling time, it is half, and sampling rate, it is double. So this is the concept of parallel processing. So this parallel processing is also known as block processing, where block is the number of samples that can be given simultaneously to the system. So in this case the block size is 2. Okay, and we can say that this is a two-leveled parallel process system. So this can be equivalently represented by a block diagram. So using a single box, this is a multiple input multiple output system, and it is a two-level parallel system. It can process two samples at same time. So let's say that sample given at this point is x0, so the corresponding output will be y0, and at same time x1 can be given to this point, and the corresponding output will be y1. After these outputs are generated, we can give new set of samples. So the sample after x0, that will be given to this port. Let's say this is port A and this is port B. Input port A, input port B. So sample given to the port A after x0 will be x of 2, and at this point it will be x of 3, and the corresponding output will be y of 2 and y of 3. After this, x of 4, and at this point x of 5, and the output will be x of 4 and x of 5. Okay, so if for single input single output system, the equation is yn equal to a of xn plus b of n minus 1 plus p of x n minus 2. Okay, so for this system, multiple input multiple output system, so for port A, because will be this will be implemented by using two SISO system in parallel, so I can write two equations. So at port A I can write y of, so because I am giving two samples at a time, so I will prefer to write the samples in the multiple of 2. Okay, so this is processing even number of samples, so y of 2k 2 into something, a even number, and this is given by a of x 2k plus b of x 2k minus 1 plus c of x 2k minus 2. Okay, so this equation is representing a one SISO system inside this, and okay, this is a one SISO system inside this, and for this system which is processing odd number of samples, I can write y of 2k plus 1, odd number, 2k plus 1 is odd number, k of x 2k plus 1 plus b of x 2k plus c of x 2k minus 1. So this is at port B. So this semi-homo system can be represented by two sets of equation. In this case, this is representing even number of samples, and this is representing odd number of samples, y. This output y represents even number of samples, and this represents odd number of samples. So now let's say this is a delay element which is employed at any point in this single input single output system. So now if the input to this delay element is, let's say, x2, okay, so the output to this delay element is the sampled came before x2. Okay, so this delay element will store the sample that came before x2. Okay, and the same will be reflected at its output. Okay, so in conventional SO circuit, if this is x2, the output would have been x1. Okay, if this is xk, the output would have been xk minus 1. But in this case, suppose this is x2, so what was the sample previous to x2? That is x0. So if the sample input to this is, let's say, x3, so what came before x3? That was x1. So this delay element will store x1, and the same will be reflected at its output x1. Okay, so I can conclude that for this system, that is two level parallel system, if the input to a delay element is x of 2k. Okay, so again I am repeating this, since this is a two level parallel system, I will prefer to represent the sample in multiples of 2. So if this is x of 2k, the output will be, okay, so here you can see that there is a difference of 2. So difference of 2 means x of 2k minus 2. Okay, so this is valid for this first system, which is processing even number of samples. And for this second one, if there is a delay element at any point and the input sample is x of 2k plus 1, even odd number of samples, so output will be, there is also a difference of 2, but these are odd numbers, these are even numbers, so the output will be x of 2k minus 1. Okay, so I can conclude that for a L level parallel system, if the input sample is x of k, the output will be x of k minus L. So this is valid for both even and odd. There is no specific generalization. This is valid for all. K can be even also, odd also. The main thing is that whatever is the value of k, the output will be k minus L. If it is even, even minus L. If it is odd, odd minus L. The difference should be L. So based on this discussion, I can conclude that if a single input single output system that is taking one input at a time and processing one output at a time, with t sampling minimum is equal to t clock minimum is equal to critical path time, that is t, is used parallelly. Let's say I am using k similar systems in parallel, so that is taking k samples from starting from 0 to k minus 1 and generating k output corresponding to this input. So the clock period t clock minimum will be equal to critical path time, that will be equal to t, that will not change. What will change is that is t sampling time. So t sampling time is t by k, so we are receiving k samples, k more samples as compared to this. So the sampling time is reduced by k and the sampling rate is increased by k times. We are receiving k samples in the same amount of time, and this is important that t clock minimum for this multiple input multiple output system is not equal to t sampling time, whereas in this case this minimum sampling time and minimum clock time are equal. And second important thing, if there is a delay element at any point in the system, so if the sample to its input is xk, the sample stored in this would have been xk minus 1, one sample previous to this. Okay, so this is xk, this is xk minus 1, this is xk minus 2, and whenever it will receive a clock, this will store in this value and will be reflected at output, and at this point there will be a new sample x k plus 1. But in a multiple input multiple output system where k similar system is employed, if the input is xn, the output will be x of n minus k. Now if I want to design this two level parallel FIR filter, so one way one way of designing this is using this kind of architecture, using this kind of one more architecture, and provide even number of samples to one architecture and odd number of samples to the second architecture. Okay, so this you can do, but you will be end up in using more number of registers, so you have to use 3 multipliers, 2 adders, and 2 delay element is used. And if you use a similar structure, then also you will be using the 3 multipliers and 2 adders and 2 delays, so total 6 multiplier, 4 adders and 4 delay will be used. So we cannot reduce the number of add and multiply operation, we have to use the same 6 number of multiplier and 4 number of adders, but we can optimize the number of shift registers if we connect these two input sources properly. Okay, so we have two different input sources. This is generating even number of samples and this is generating odd number of samples. Okay, so and the output corresponding to this is y of 2k, even number of samples, and this is y of 2k plus 1. Okay, and this same 3 number of multipliers, 2 adders, and 3 number of multipliers and 2 adder in this. Okay, so now I will be connecting the inputs in such a way that the number of delay element will be optimized. Okay, so first implementing this filter. Okay, so this is a into x of 2k. Okay, so I have 2k at this point, so I can connect this 2k to this multiplier, and the input, second input will be a. Next is x of 2k minus 1. Okay, so this 2k minus 1 can be generated by using a delay element at this point. If I use a delay element and the input is x of 2k plus 1, so the output will be x of 2k. Since this is a two level parallel FIR filter, so the difference will be of 2, so 2k minus 1, and this I can connect to the second multiplier, and the multiplication factor b can be given to the second input of this multiplier. This is 2k minus 2, so this can be generated by delaying this input signal. So a delay element d, and output will be x of 2k minus 2, and this can be given to this multiplier, and the second input is c. Okay, so this is e of x of 2k, c into x of 2k minus 2, this term, and this is b into x of 2k minus 1. Okay, so this is implemented. Now to implement this, we can connect this inputs in the similar manner. Okay, so the first term a of x 2k plus 1, so this is 2k plus 1, so directly connecting x of 2k plus 1 to this multiplier, and the input can be the constant a is given to the second input of this multiplier. The second term is x of 2k, so I have x of 2k at this point, so I can directly connect x of 2k from this point. So this is x of 2k, and the multiplication factor is b, so b can be given to the second input, and at this point I need x of 2k minus 1, so I have x of 2k minus 1 at this point, so I can connect this directly, and the second input will be, that is c. Okay, so I have drawn it in a more proper way. So here you can see that by connecting the circuit in a different manner, you can avoid using two extra delays, so only two delays are used. Okay, otherwise in conventional form, using the SISO system, just using parallel form, four delay elements would have been used. So by connecting it appropriately, you can avoid using two extra delay element.